What about this problem? We're asked here to find the length of this bronze rod in order for the steel and bronze to reach their capacity simultaneously. So, how do we do that? This is it. So, we say that if they reach their capacity simultaneously, considering steel, our tau actual of steel, which is TR over J, this is for steel, will be exactly equal to the tau allowable. So the torque in steel times the R of steel, the radius of steel, since the diameter is 50, so this is 25 over J. J is pi over 32 d to the fourth. 50 to the fourth. This must be exactly equal to tau allowable, that is 100. Okay? So from this, we will get the torque in steel is going to be, so this is going to be equal to 2454,369 Newton millimeter. So this is the same as 2.454 kilonewton meter. Kilonewton, 1,000 Newton meter is 1,000 millimeter. 1,000, that is 10 to the 6. You get it? Now, considering the bronze, our bronze is going to be the tau in bronze actual, which is TR over J in bronze, must be exactly equal to tau allowable in bronze. So the torque in bronze times the radius of bronze, that is half of this, 37.5 over J, which is pi over 32 d to the fourth. 75 to the fourth is exactly equal to 70. So, solving the torque in bronze, this is going to be, this is 5.798 kilonewton meter. So, this will be the torque in steel and bronze at exactly their capacity. Now, the key equation here, take note that we have here the total theta total, that is the theta from A to C, because this is fixed, whatever the rotation in between, but the rotation of C relative to A is 0 because they are not moving. So, theta A relative to C is 0. Theta AC is theta AB plus theta BC is 0. Wherein rotation in this direction, positive. Okay? Now remember, if I will draw here my torque diagram, so the torque in steel will be the same as TA, the torque in bronze will be the same as TC. Let me do that. So this is our torque T. Naturally, this is TA, this is TB. I am using a double arrow notation for torque. This means a torque in that direction. This means a torque in this direction. So, this is going to be our torque diagram. I will be drawing left torque, meaning torque in this direction, negative. Right torque, torque in this direction, positive. So, we will go down from 0. We will go down here by TA. And there is no torque between this and this, so it would be like this. Then here, we will go up by T, so plus T, it will move up. So this is T. Then from here to here, there is no additional torque, so it will be horizontal. Here, there will be torque TB that will bring it back to 0. So this is TB. So this is the torque in steel, while this is the torque in bronze. Right? So as you can see here, this is negative, meaning torque to the left. This is positive, meaning torque to the right. So, taking torque to the right positive, torque to the left negative, this is theta in steel. So, the theta in steel plus the theta in bronze is equal to 0. But this would be negative because it is a torque to the left. So, if this is negative, you move it to the right, we will have here the theta in steel is equal to the theta in bronze. Okay? But what is theta? So, the theta in steel is equal to TL over JG in steel, while theta in bronze is TL over JG in bronze. Right? Okay? So, substituting, because the T in bronze and steel are at their full capacity, we substitute them. This is going to be T in steel, 2.454 times the length of steel, 2 meters, over J, pi over 32, D to the fourth, 50 to the fourth, G, 83. I won't pay attention to the units anymore. Anyway, the units left and right are just the same, so they will just cancel out. So this will be the maximum torque in bronze, that is 5.798 times L in bronze over JG pi over 32 D to the fourth 75 to the fourth times G 35 gigapascal. So we will have here the length in bronze. The length in bronze, so that they will reach their capacity at the same time, will be, this is 1.807 meters. So this is the length in the bronze rod. You follow? Okay. What about this problem? We are asked here to find the maximum torque T if the length of the bronze is 3 meters. This time, take note, the allowable stress in steel and in bronze will not or may not necessarily reach their capacity at the same time. So, we know that the capacity will be reached at the same time. We call it a balanced condition or 100% efficiency if the length of bronze is 1.807. But if the length of bronze is 3 meters, what will happen? Okay, this is it. So, we want here to find the maximum torque T that can be applied at the junction. So, if we take summation of moment or torque about the z-axis or longitudinal axis is 0, the z-axis is this longitudinal axis. So, we have here T minus TA minus TC is equal to 0. But your TA is the same as T in steel. Your TB is the same as T in bronze. So we say here that T is equal to T in steel, the absolute value, plus the T in bronze, the absolute value. You get it? So let us call this as equation 1. So in order to solve T, we need the torque in steel, the absolute value, plus the torque in bronze, the absolute value. Okay? So the one with a sign are TA and TC. But the torque in steel and bronze are the absolute value. Okay? Now, in here, however, torque in steel is not necessarily this one, and the torque in bronze is not necessarily this one. One of them will be reached this time, but the other will not be maximized. Why? Because this will be reached at the same time, this optimum or maximum that will bring steel and bronze at its allowable shearing stress when the length of bronze is 1.807 meters, as in our previous problem. But this time, it is 3 meters. You get it? So, let me explain further. Okay. Now, we said, isn't it, that from A to C, the theta is 0. From where we obtain that the theta in steel will be equal to the theta in bronze. But theta we know is TL over JG. This is in steel. So this is TL over JG in, this is in bronze. So making the substitution, this is the torque in steel. The length of steel is 2 meters. The J of steel is pi over 32. Diameter to the fourth, 50 to the fourth. Times G, that is 83. Okay? I am not paying much attention to consistency of units. Anyway, on the right side, the units are the same as the units on the left side. So, they are still consistent. Okay? So, this is the torque in bronze times the length in bronze is 3 meters over J, pi over 32 d to the fourth, 75 to the fourth times G, 35. This time, I will have an equation between TS and TB. So, pi over 32 may be cancelled out. So, solving TS in terms of TB, all of this divided by all of this, you'll get your TS is equal to 0.70265 of TB. Let me call this equation as equation number 2. So the relationship of TS and TB will always be this one with 2 and 3 meters length of steel and bronze respectively. You get it? Okay. So it means if I'm going to consider that steel reach its capacity first. If we assume that steel reach its capacity first, meaning that is TS is equal to 2.454 kilonewton meter. But this time, substitute this to equation 2, this one. Your TB is going to be TS over 0.70265. So, we substitute this here. Our TB is going to be 3.494925 kilonewton meter. Notice that this is less than the capacity of bronze. And TS cannot exceed this one. In order for TB to increase, TS must increase. As TS increase, TB increases also, right? So, but TS cannot be more than this because this is it's just capacity. It means the steel governs the design. You follow? Look here. If I will assume, just for comparison, that bronze reach its capacity first, that is T in bronze is 5.798. So substituting this to equation 2, the T in steel is going to be 0.70265 of T bronze. We substitute this here. The T in steel is 4.074 kilonewton meter, which is already more than the T steel capacity. Meaning, this will result already in failure of steel. You follow? So, this one, this is less than capacity of bronze. So, this is safe. While steel is already at its critical level. So therefore, we just substitute to equation number 1, this one, the torque that can be applied is going to be T in steel plus T in bronze. And this is 2.454 plus 3.4925, and this is 5.9465 kilonewton meter. So this is going to be the maximum torque that can be applied at the junction without exceeding any allowable stress of steel and bronze or bronze, no? And take note that in this design or in this situation, steel governs the design. Okay? Now, it is logical to think that bronze will control the design when your L is less than 1.807. You get it? Because when L is greater than 1.807, like 3, steel controls the design. But when this is less than 1.807, let us say 1 meter, then it will be bronze that will control the design. You get it? Okay? So let me show how it goes. This time, our length of bronze is 1 meter. So what is that maximum safe torque T at the junction that can be applied without exceeding this allowable stresses? So, using the equation theta S is equal to theta of bronze, so you have here, this is 2 meters, this is 1 meter. So, computing this, all of this divided by all of this, you'll get your TS is equal to, so this is 0.2342 T of B, T in bronze. So let me call this as equation number 2. Okay? So if I will assume that steel will reach its capacity first, meaning TS is equal to this. Now, substituting this to equation 2, this one, you'll have the T in bronze is equal to the T in steel over 0.23422. I stored in my calculator the more exact value of this, the one containing 10 digits. So, substituting 2.454 for this, you'll get the T in bronze is equal to 10.48 kilonewton meter. But this value is greater than the T capacity of bronze. Before you reach this T in steel, you will already reach the T in bronze. So the bronze will reach its capacity first. So my suggestion based on logic that bronze will yield first when length of bronze is less than 1.807, the balance length, then that theory or concept is correct. So therefore, in here, bronze will yield first. So it will control the design. So when T in bronze is equal to this, we substitute this to equation 2. The T in steel is 0.23422 of T in bronze. You substitute this here, you'll get, so this is going to be 1.36 kilonewton meter. Notice that the torque in steel is less than its capacity. So this is less than the capacity of steel, which is 2.454, meaning bronze will really reach its capacity first. So substituting to equation 1, therefore, the total torque is going to be the T in steel plus the T in bronze. So this is going to be 1.36 plus 5.798. So therefore, T is going to be, so this is 7.156 kilonewton meter. Did you get it? What about the torque in hollow rod? Let us have this one. A hollow rod has an outside diameter of 100, meaning radius is 50, and inside diameter of 75, meaning radius is 37.5. Rod is 2 meters long, G is 83 gigapascal, allowable shearing stress 100 megapascal. We are asked here to find the maximum safety. So, if maximum safe is being required, then we use the equation of safety. So, the equation of safety simply says, in order to be safe, so there is only one allowable stress given, that is of shear stress. So, to be safe, our T actual maximum, which is given by TR over J. So, T is T max, R is R max, J, of course, is J. So, must be less than equal to tau allowable. So, therefore, our T maximum, the R maximum from the centroid, this is the centroid, and this is what is required, the maximum torque T. So, T max times R max, from the centroid, the element farthest from the centroid are the elements farthest to the centroid. They are the elements at the outer circle. So, this must be R outer. Over J, Rj is pi over 32. It's the J of the big circle minus the J of the small circle. So that is pi over 32 d to the fourth minus small d to the fourth. So I will just use big R to indicate R of the outer circle. Must be less than or equal to tau allowable, which is 100 megapascal. So substituting the values, we have here T max. R is 50 millimeters over pi over 32. D to the fourth, this is 100 to the fourth minus D 75 to the fourth. Must be less than or equal to 100. So therefore, our T max is going to be equal to or less than 13.422 kilonewton meter. So this is the maximum safety that this rod can support without exceeding this allowable stress. When your torque is this one, the stress in the rod is 100 megapascal. Okay? Alright. What about this question? If the rod is subjected to a torque of 10 kilonewton meter, that is less than this, L is 2 meters, G is 83 gigapascal, we are asked to find the minimum shearing stress, the maximum shearing stress, and the shearing stress at 40 mm from the center. Now we know here that our shearing stress tau is equal to TR over J. Our R here is the distance of element that is a point in the rod from the centroid of section. So if we are looking for tau minimum, then R must be R minimum. So this is going to be the torque 10 kilonewton meter, that is 10 times 10 to the 6 Newton millimeter. The minimum distance of any element of this rod or section from the centroid is going to be R minimum, which is 37.5. All over J, the J is pi over 32. J of the outer circle pi over 32 d to the fourth minus pi of the inner circle pi over 32 d to the fourth. So substituting for d the value of 100, for small d the value of 75. So this is going to be, so this is 55.88 megapascal. So this is your tau minimum. While our tau maximum must be equal to TR max over J. And this is 10 times 10 to the 6. The R max, the maximum distance or farthest distance of any point on the section from the centroid is the R maximum, which is 50, R outer. So this is going to be 50 over J, pi over 32, 100 to the fourth, minus 75 to the fourth. And this is 74.5 megapascal. You get it? Now, our tau at 40 mm away from the center, this is 37.5. The stress here, the stress here, the stress here, 40 mm away will be T times 40 over J. So this is 10 times 10 to the 6 times 40 over pi over 32, 100 to the fourth, minus 75 to the fourth. And this is 59.6 megapascal. You follow? Okay. Let us go to flange bolt couplings. When two rods are to be connected mechanically, then we use a flange in order to connect them. So this flange will either be also bolted or welded to the rod. Then the two rods with the flange will be bolted together. Normally, this is being used in connecting water lines because you cannot do welding on site. You can only do mechanical connection, wherein threading may not be applicable because of the limited capacity or strength that thread will offer. Okay, so we use flange bolt coupling also for easier repair and maintenance. Okay, so in this situation, the torque being applied on the rod will be transferred to the flange, and the flange will transfer it to the bolts. Then the bolts will transfer it to the other flange, and the flange will transfer it to the rod to resist the torque. You follow? So our focus here is the strength of the bolts in the flange supporting the torque. So let us have this one. A flange bolt coupling consists of 12 pieces of 20 mm diameter bolts that are evenly spaced in a bolt circle that is 450 mm diameter. So the diameter of this is 450. So meaning the radius, the distance of each bolt from the center is 1/2 of 450. This is 225 millimeters. So this is 225, 225, 225. So we are asked here to find the torque T that we can apply without exceeding the stress here of 100 megapascal. Now, because this torque is counterclockwise, each bolt will react. And the reaction of the bolt must produce a clockwise moment. So this would be the force in the bolt, but let me express that in terms of stress. So this would be the stress in the bolt, this is stress in bolt 1, bolt 2, stress in bolt 3. So all of them will be clockwise. Okay? So in as much as stress is equal to TR over J, this is J about the global centroid of 12 bolts. Because it is the bolts that are supporting the load. So, therefore, in here, this must be less than or equal to what? It must be equal or less than to the allowable stress. So, we are asked here to find the torque. So, this is T. The R, what is the R? Our R is going to be from here to here. That is 225. Regarding the J is, take note the J of this bolt about its centroid is what? Its J is pi over 32 d to the fourth, right? So d to the fourth, diameter of bolt, which is 20. But we need the J about the centroid of all the bolts, or we call it the global centroid. So we transfer it from local centroid to global centroid. So plus area times the transfer distance squared. This is the transfer formula for inertia. But this is only for one bolt. And there are 12 of them. So we multiply this by 12. So this is J global of the 12 volts. Okay? So must be less than or equal to the tau allowable, which is 100. You get it? Okay. So we substitute, we have T times 225 all over pi over 32, diameter 20 to the fourth, area pi over 4, 20 squared, transfer distance from local to global, that is 225 squared, multiplied by 12. And this must be less than equal to 100. So therefore, we will be able to solve the torque. And the torque must be less than or equal to 84.91 kilonewton meter. Do you follow? What about this one? A flange bolt coupling is supported by bolts 16 mm diameters in two bolt circles, concentric bolt circles. One is 250 mm diameter, the other is 400 mm diameter. If it is subjected to a torque of 100 kilonewton meter, so let us say that that torque is this one, this is T, this is counterclockwise, then each bolt will react to produce a clockwise moment about G. For example, the outer bolts. So, its distance from the center is this. So, it will produce this stress. Okay? So, this is the stress in the outer bolts. So, this is the stress in the outer bolts. So, the direction of stress, if you multiply this by the area, it will be the force. So, the direction of the stress is perpendicular always to its distance from the centroid. This is its R or its C. This is tau outer. This and this are equal because their distance from the centroid are equal or are the same. Because we know that stress is simply TR over J. This J is J global of all the bolts resisting the torque. So the stress is dependent upon the R. If their R are the same, their stress are also the same. So the stress in outer rivets or outer bolts will be the same because their R are the same. Let me just first solve the J global. The J global is going to be the summation of J local, J of each bolt, plus area transfer distance squared. So the J local, for example, of this is pi over 32. D to the fourth, area of bolt is pi over 4 times this diameter squared times distance squared. You get it? But don't memorize this. It's just this one. So, beginning with this outer bolt, its J is pi over 32. The diameter is 16, so this is to the fourth. Plus area the area is pi over 4 diameter. So that is 16 squared. So transfer distance from the local centroid to the global centroid, if this is 400, this must be 200. So this is 200 squared. This is for 1 bolt. And there are 1, 2, 3, 4, 5, 6 of them. So times 6. However, you still have 4 bolts in the inner circle. So this is pi over 32 d to the 4th plus area pi over 4, 16 squared, transfer distance squared. Since this is 250, the radius is 125. So from local centroid to global centroid, that is 125. So 125 squared. This is for 1 bolt. And there are 4 of them. So therefore, multiply this by 4. So we will be able to compute here the J global. And J global equals 60.886 times 10 to the 6 millimeters to the 4th. So substituting here now, our shearing stress in the outer bolts is T. Our T is 100 kilonewton meter, so that is times 10 to the 6, times the R outer is 200. So 200 over J, that is 60.886 times 10 to the 6. And this is 328.485 megapascal. While tau in the inner bolts will be T R in over J. So the torque is 100 times 10 to the 6 multiplied by R in. This is 250. R in is 125. 125 over J, 60.886 times 10 to the 6. And this is, so this is 205.3 megapascal. Do you understand? You follow? Okay. Let us solve this one. We have here a plate that is 10 millimeter thick, and it is attached to another steel element, this one, by 5 pieces of 20 millimeter diameter bolts. So this plate is subjected to this torque of 20 kilonewton, pair of 20 kilonewton force, 350 millimeter distance. So therefore, the torque is simply P times the distance. So 20 kilonewtons times the distance is 350 mm or 0.35 meter. So this is 7 kilonewton meter. Now, since this is counterclockwise, each bolt will react to produce a clockwise moment. And the centroid of these 5 bolts by inspection is here, right? So this is the G. So each bolt will react to produce clockwise moment about the G. This bolt, for example, let me call this bolt 1, bolt 2, bolt 3, 4, and 5. So the distance of bolt 4 from G is this one. So the clockwise moment will be this one. So this is going to be the stress in rivet 4. Okay? So this is the R of rivet or bolt 4. Bolt 5 will produce a clockwise movement about G also. So it will be this one. Its distance from G is this one. So this is the R of bolt 5. So this is going to be the tau of bolt 5, perpendicular to R. On the other hand, for bolt 2, its distance from G is this one. To produce a clockwise moment, it must be something like that. So the direction must be upward. So this is tau in bolt 2. So this is R in 2. Notice that R2 and R4 are equal. They are both 70. Now, the distance on the other hand of bolt 1 from the centroid is this one. So this is going to be your R1. And that is 70 plus 70, 140. So, therefore, to produce a clockwise moment about G, it must be upward. So, this is tau 1. You get it? So, notice that R1 and R5 are equal. So, it follows that tau 1 and tau 5 are equal. You get it? And the distance of bolt 3 from the centroid is 0. So, meaning the stress at point 3 is 0 because it is at the neutral axis or global centroid. Okay? So, computing the stress, we know that stress is what? TR over J global. Let me first solve the J global. The J global is summation of J local plus area distance squared. And our J local is pi over 32 d to the fourth. So let me solve it. So this is going to be pi over 32 d to the fourth. The diameter of bolt is 20 to the fourth. So let me begin with bolt 1. So plus area transfer distance squared. The transfer distance of bolt 1 to the global centroid is 140. So plus area pi over 4 diameter squared, transfer distance 140 squared, right? This is for bolt 1. But bolt 1 and bolt 5 are of the same distance 140 from the centroid. So I just multiply this by 2. So plus, considering bolt 2, it would be pi over 32, 20 to the fourth, plus area, pi over 4, diameter squared, transfer distance squared. The transfer distance is 70. So 70 squared. And there are two bolts whose distance from the centroid is 70, 2 and 4. So we just multiply this by 2. Lastly, bolt 3. Pi over 32, 20 to the fourth, plus area distance squared. The transfer distance from local to global is 0. So no need to transfer. So this one has no area distance squared because its transfer distance is 0. So computing all of this, you'll get here, J global is going to be 15.472 times 10 to the 6 millimeters to the fourth. So solving now our tau, our shearing stress at bolt 1, which is the same as shearing stress as bolt 5, because their distance from the centroid are the same, both have a distance of 140. So this is going to be TR1 over J global. Our torque is 7 times 10 to the 6 Newton millimeters. R1 is 140 over J global. The J global is 15.472 times 10 to the 6. So this is 63.34 MPa. Now, the shearing stress in rivet or bolt 2 is the same as tau in bolt 4 because their distance from centroid are the same, both equal 70. So this is TR2 over J global. And this is 7 times 10 to the 6 times R, which is 70, over J global, 15.472 times 10 to the 6. And this is 31.67 MPa. While the tau in bolt 3, we say that this is TR3 over J global. Since its distance from the centroid is 0, so this must be 0. You follow? You get it? So the arrangement of bolts need not be circle. It may be straight, rectangular, or whatever shape. Just They only differ in the computation of J global. Pi over 32d to the fourth plus area distance squared. Summation of all of them. You get it? What about the second situation? The motion impends to the left, meaning this is to the left downward, this is to the left upward. If that is the case, our friction is to the right. This is the friction at A. This is to the right. This is the friction at B. It means that our R between this and this is going to be our RB, and the angle between them is the phi. So from the vertical to normal, this is the same as this angle of the incline. This is 60 degrees. So RA makes an angle of 60 plus phi. This is the phi of angle B, which is equal to 5.71. 60 plus phi B, this is 65.71 degrees. So RA is between FA and NA, so it must be this one. This is RA. And the angle between RA and the normal is the phi at A, which is 11.31 degrees. So if this is 30, this is 30, so from the vertical to normal is 30, so this must be 30 minus 11.31. So this is 18.69 degrees. Okay? So if we will draw the force triangle for block A, starting with WA, it is this one. So this is WA, which is 1962 newtons. And at the tip of this, we connect our T. Our T makes an angle of, if this is 30, this is 60 degrees. T makes an angle of 60 degrees with the vertical. And then at the tip of this, we connect our RA. RA makes an angle of 18.69 degrees with the vertical. So therefore, this angle must be 180 minus this minus this. Minus 60 minus 18.69 degrees. This is 101.31 degrees. Now, if we will apply now sine law, we therefore have here T over the sine of the angle opposite, 18.69, is equal to 1962 divided by the sine of angle opposite it, 101.31 degrees. You get it? So from here, you'll be able to get your T, and T is going to be 641.17 newtons. Now moving to block B, taking the FBD of this, starting with WB. So this is our WB, and WB is 9.81 MB. MB is a known. At the tip of this, we connect our RB. Our RB makes an angle of 65.71 degrees with the vertical. So this is 65.71 degrees. And at the tip of this, we connect our 2T. Our 2T is twice of this, which is 1282.34 newtons. And it makes an angle of how much with the vertical? This one. If this is 60, then this must be 30 degrees. This is 30 degrees. So therefore, this one is 180 minus 30 minus 65.71 degrees. And this is 84.29. So applying sine law again, so we will have here this one over the sine of opposite, 9.81 MB over the sine of the angle opposite, 84.29 is equal to 2T which is 1282.34 over the sine of angle opposite 65.71 degrees. Okay? So, therefore, solving our MB is going to be, so this is 142.7 kilograms. This is the mass of B, so that our motion impends to the left. You get it? Okay. Let us have this example. So we have here this beam loaded by 20 kilonewton and 40 kilonewton load. We are asked to draw the shear and moment diagram, and in the process we'll be able to get the maximum shear, the maximum moment, which are crucial and important in designing the beam. So in here, first let us solve the reactions. So the reaction can be solved by taking summation of moment at D is equal to 0 clockwise positive, counterclockwise negative. So I have here minus 40 times 2 minus 20 times 5 plus the reaction at B, this one, will produce clockwise moment at D. So plus RB multiplied by the moment arm 4. And this is equal to 0. So therefore, our RB is going to be 40 times 2 plus 20 times 5 divided by 4. I also have the what I so-called the U method. If this is your moment, if this is your point where you'll take the moment, so you just turn from here, then back there. So it would be the distance times the force, the distance times the force divided by the distance. Okay? So force times distance, 4 times distance, moment over distance. So I have 40 times 2, 20 times 5 over 4. That is RB. You get it? You follow? Okay. Or you have here 20 times 5, 40 times 2 over 4. That is your RB. You get it? Okay. So RB is going to be, this is 45 kilonewtons. And your RD must be 20 plus 40 minus RB. RB is 45, so this is going to be 15. So this is your RD, which is 15. Let me reflect it here. So this is 15, this is, so let me reflect these values here. RD is equal to 15 and RB is equal to 45. So let me now draw our shear diagram. Notice that the symbol for shear is V, that is the V diagram. So let me write here the V ordinates. So the reason why it is called V diagram or shear diagram, it is simply diagram of vertical forces. Okay? Alright. So this is merely summation of vertical forces. So at this point, starting with 0, you will go down by 20. So this is minus 20. So 0 minus 20, this is minus 20. And then, from here to here, there is no vertical force, so this remains horizontal. When it reaches B, it will go up by 45. So this is plus 45. So this is plus 25. So this is going to be plus 25. From here to here, there is no vertical force, so this remains horizontal. When it reaches this point, there is 40 down, so minus 40. So this is minus 15. Okay? So it will go down here to minus 15. From here to here, there is no vertical force, so there is no change in diagram value. So at this point, we will go up by 15. So this is plus 15. So this is 0. The initial must be 0. The final must also be 0. So this is going to be your shear diagram. Do you follow? So the maximum positive shear is 25. The maximum negative shear is minus 20. Okay? Now let us draw now our moment diagram. let me write here our moment ordinates. I'm just writing it, but as you master it or as you learn it, you can do without this one, direct in your calculator, okay? You will know that your computations are correct when it ends to 0 again, okay? Alright, provided that it is, of course, an external hinge support. It will end up with 0 moment, okay? Alright, now, starting with 0 here, 0 plus the area of this is the shear here. So this is 0 plus the area of the rectangle is 1 times minus 20, right? So this is going to be minus 20. So the moment here is going to be minus 20. This is 0 degree, so from here to here must be first degree. That must be a straight line. You follow? Now, from here to here, minus 20 plus the area of this is the moment here. So it would be plus. The area of this is 2 by positive 25, which is 50. Minus 20 plus 30. So the moment here is going to be plus 30, right? So in here, from here to here, take note that this is 0 degree horizontal. From here to here must be first degree. It must be a straight line. You follow? Okay. So in here, we have 30 plus the area of this is the moment here. So plus 2 times negative 15. This is negative 30 plus 30, back to 0. This is 0 degree, so from here to here must be first degree or straight line. You follow? So the maximum moment, positive moment is 30. The maximum negative moment is minus 20. The maximum positive shear is 25. The maximum negative shear is minus 20. You follow? Okay. Let us have this one. In this particular problem, we want here also to draw the shear and moment diagrams. Let us first solve the reactions. This is our RA. This is our RD. By taking summation of moment at point D is equal to 0, clockwise moment positive, I have RA times 8 minus 40 times 6 plus 20, no multiplier for 20 because it is a moment, is equal to 0. So therefore, our RA is going to be, so this is 27.5 kilonewtons. So if we take summation of forces along Y equals 0, upward force is positive, I have RA 27.5 plus RD minus 40 is equal to 0. This will not be part of the forces because that is a moment. So therefore, our RD here is going to be 12.5. Okay? So RD here is 12.5. Let me write here our shear ordinates starting with 0. So let us say that this is my V-axis. Starting with this, I will go up by 27.5. So plus 27.5, so this is the shear. So from here to here, there is no additional load, additional vertical load, so this remains horizontal. Then at this point, we will go down by 40, so minus 40. So this is minus 12.5. So this is going to be minus 12.5. So from here to here, there is no vertical load, so there is no change in value of vertical force. So at this point, we will go up by 12.5. So this is plus 12.5. So this is 0. So this is going to be our shear diagram. Okay? So this is a positive area. this is a negative area. Let me draw our moment diagram. So, this is our moment coordinates. Okay? So, you have here, starting with 0, 0 plus the area of this is the moment here. So, plus 2 times 27.5. And this is going to be equal to 55. So, the moment here is going to be positive 55. This is 0 degree. This must be first degree. Okay? So, 55 plus the area of this, I will stop here because there is an applied moment here. So, 55 plus the area of this is the moment here. So, plus negative 12.5 times 3 meters. Okay? So, this is 55 minus this. So, this is positive 17.5. So, the moment here is positive 17. This is positive 17.5. This is 0 degree. This must be first degree. But at this point, there is an applied moment. Right? So, as far as clockwise moment is concerned, with respect to D, that would be an upward moment or positive moment. So, it would be plus 20. So, this is plus 37.5. So, we are going to go up. This is now positive 37.5. And this is 20. You get it? So, 37.5 plus the area of this must be the moment here. So, plus, it would be 3 meters by negative 12.5. So, therefore, this is going to be, it must be 0. So, the moment here must be 0. So, from here, this is 0 degree. This must be first degree. So, the maximum positive moment is 55. There is no negative moment. Do you follow? You get it? I want to emphasize one thing here. The point of maximum moment is the point where shear becomes 0. The point of maximum moment is the point where shear becomes 0. The point of maximum moment is the point where shear becomes 0. Point of 0 shear is a point of maximum moment. The point of maximum shear is a point where there is a change of load. You get it? You follow? Okay. Let us solve this problem. We are given here this shear diagram, and we are asked to find the reactions at supports C and E, and the value of distributed load and the maximum moment of the beam. So let us do this. Now, let us first solve our load diagram. The load diagram will be done backwards. Now, so starting with A for our load diagram, so this is the load diagram axis or the beam itself. Starting with 0, we know here that when we write our shear ordinates, the shear at A begins at 0. 0 plus the area of the load diagram is equal to the shear at B, right? So, this is 0 plus the area of the load diagram is equal to the shear at B. But the shear at B is negative 10. So, this is negative 10. And since this is first degree, it means that the area here is 0 degree. It must be a uniform load. So, first degree, it means this must be 0 degree. So, if the uniform load has a magnitude of W rectangular, so the area is simply minus WR, minus because it is downward, multiplied by 2 meters. So that is times 2. So the value of WR is going to be equal to 5 kilonewtons per meter. Okay? So let me reflect the value here. So this is 5 kilonewton per meter. Now from here to here, there is no change in shear. There is no change in vertical force, meaning there is no additional vertical force from B to C. Okay? So this is also the shear at C, which is the same as the shear at B. Then, from here, it went up by, this is 10, this is 5, it went up by 15. So meaning there is a vertical force here which is 15. So take note that it is mentioned that it is a support. So most likely it is a roller support here. So this is the value of your RC, which is 15. From here to here again, there is no change in vertical force. So it means there is no load from here to here. Then here there is a second degree curve. From the drawing, this is a point of tangency with horizontal. So meaning this portion is a spandrel area. Second degree spandrel area. If this is second degree, then the curve here must be first degree, right? So, and this is increasing, right? So this is going up. So it means this is a positive area. You get it? Now, we will have to look for our diagram here. Then, the similar to this is equal to this one, meaning it is a positive load increasing. So, starting with zero slope, the slope here is 0, the value here is 0. First degree load, and this is positive increasing. Positive load means upward load, right? And let me compute here the value of W triangular, this one. So from here, where the shear is positive 5, plus the area of the load diagram is equal to the shear at the other point, which is plus 20. So therefore, the area of the load diagram, which we now know as a triangle, is 1/2 of 2 times W triangular is equal to 20 minus 5, 15. So therefore, WT is 15. So this is 15 kilonewtons per meter. You get it? So this is our load here. But there is, take note here, a 20 vertical line here. So it means there is a reaction here of 20. So most likely that is the reaction at E. Do you follow? So this is 20 kilonewtons, but this is downward. You get it? Okay. Let me now draw our moment diagram. So this is our moment diagram axis. The moment diagram axis will now be simple. So starting with 0 here, 0 plus the area of this, but this is a negative area, positive area, right? So in here, 0 plus this area, but this area is 1/2 of base 2 times the height. The height is negative 10. So this is negative 10. Okay? So this is negative increasing. Negative increasing is this one. So the curve must be something like this. It started with 0. It starts with the tangency with the horizontal. So it would be something like this. And this is negative 10. And let me repeat, this must be a second degree curve. So minus 10 plus this area is the shear here, is the moment here. So it would be plus, this area is 2 by negative 10. So this is going to be minus 30. So the moment here is minus 30. This is 0 degree, so from here to here must be first degree. Okay? Now, from here to here, the moment here plus this area is the moment here. But this is a positive area, so plus 2 by positive 5. Okay? So therefore, this is minus 20. Okay? So our moment is minus 20. It must be somewhere here, right? This is 0 degree, so from here to here must be first degree. And this is minus 20. Minus 20 plus this area is the moment here, right? And that is, what is this? 2 by 5. So this is plus 2 by 5, the area of this rectangle plus the area of this spandrel. This is second degree spandrel, so that area is 1/3. So this is second degree, area is 1/3 base height. 2 by, this is 20, this is 5, so this is 15, right? Okay? So 1/3 of 2 by 15. So computing this is going to be minus 20 plus 10 minus 10 plus 10. Minus 10 plus 10, so this is going to be 0. So the moment here is going to be 0, right? So therefore, what we will have here will be second degree, this must be third degree. From minus 20 to 0, it must be third degree. But what is the curvature? Is it concave upward or concave downward? Let us see here. So this is positive increasing. Positive increasing is this, right? So it looks like something like this. But it didn't begin with 0, it begins with 5. So it will not begin here, it must be somewhere here. So it must be something like that. So from here, it begins with this. But this is a third degree curve. You follow? So therefore, this is your moment diagram. So all our moments from here to here, they are all negative. So meaning the beam really bends downward. You get it? So most likely here, this would be a roller support. That's why the moment is also 0. You follow? What about this one? We are asked here to find the reactions at support C and E. And also, we want the values of the load and the moments. So, let us begin with this. So, this is our shear diagram. So, this is first degree. This curve is second degree. Obviously, from the figure, this is a point of tangency with the horizontal. So this one, if we will project, is a spandrel area. But this one is not a spandrel area because this is not a point of tangency with the horizontal. Okay? Alright. So, starting with this, writing our shear ordinates. In computing the shear ordinates, starting with 0. 0 plus the area of the load diagram from A to B is equal to the shear at B. This one. And the shear at B is minus 15. This is first degree, meaning the load here is 0 degree, meaning horizontal. So it must be a uniform load. This is going down, so it means the load is negative, right? Negative meaning downward load. So let us call this W rectangular. So the area of this is equal to 2 by WR. So 2 by WR is equal to the shear at B minus 15. So therefore here, our WR is equal to minus 15 over 2 minus 7.5 kilonewton per meter. So this is minus 7.5 kilonewtons per meter. Okay? Now, so from here to here, there is no change in shear. So from here to here, there is no change in load. But here, take note, there is an upward force or upward line, which is 15 minus 5. This is 10, right? Correct? So meaning there must be an upward or vertical force here, which is 10. And this is your RC, which is 10. So most likely this is a roller support. Now from here to here, there is no change in vertical force. So therefore, there is no additional vertical force from here to here. But when it comes to here, from here to here, there is an increase, right? And it is second degree. If this is second degree, the load diagram is first degree, right? If it is first degree, meaning it is triangular load. But take note of the curve, this one. It is going up, looking at the Padilla's chart or Padilla's cusp. The one that is similar to that is this one, positive decreasing. But it is first degree. Positive decreasing, so it must be something like this. Take note that this is a point of tangency with horizontal, so the value of the load here must be 0, right? It reached this point, right? The point of tangency with horizontal, so it means it is a triangular load decreasing. So it is positive, meaning it is a load that is going up. Let us solve our W triangular. So the shear here plus the area of this is the shear here. So it is minus 5 plus the area of the load diagram from D to E is equal to the shear here, which is positive 25. So the area of the load diagram is a triangle 1/2 of 3 by WT is equal to 25 plus 5, 30. 30 over 3, 10 times 2. WT is 20 kilonewtons per meter. Okay? So this is equal to 20. Right? So we are done with the load diagram. Okay? And at this point, there will be a downward trend of 25. So therefore, there must be a vertical reaction here. This is RE, which is 25. So let us draw now our moment diagram. So writing our moment ordinates, starting with 0, 0 plus the area of this is the moment here. So that would be the area of this is 1/2 of 2 by minus 15. So this is going to be minus 15. So the moment here is equal to minus 15. This is first degree. From here to here must be second degree, right? And this is negative, negative increasing. Negative increasing is this one. So it must be something like this. So it begins with 0. So it begins with point of tangency with the horizontal. So this is second degree, right? Minus 15 plus the area of this is the moment here. So, but the area of this is 1 by minus 15. So plus 1 by minus 15. So this is minus 30. Okay? This is 0 degree. From minus 15 to minus 30 must be first degree. So this is minus 30. Minus 30 plus the area of this, which is also negative. So, is equal to the moment here. So, that is 1 times minus 5. So, plus 1 times minus 5. So, this is minus 35. So, our moment here is going to be minus 35. And this is 0 degree. So, this must be first degree. Okay? So, let me just put it here. So, this is first degree. Okay? So, this is minus 35 plus the area of this. But take note that it is composed of two areas. One negative, the other positive. Right? You get it? Okay. This area cannot be solved by simple formula for spandrel because it is not a spandrel. Okay? So, my suggestion is this. Instead of using the area concept, I will just use the moment. Okay? Take note that this is the point of zero shear. Let us call this as Z. Let us locate where the point of zero shear is. Let me call this point D, E. Let me call this point as point F. This one. The point of zero shear. So, going to this, it would be here. The point of zero shear. And this is Z. It means that this must be 3 minus Z. Okay? Now, take note using Y is mx formula for this triangle. So, this quantity from Y is mx. This is equal to m, the slope of this, 20 over 3 times the x. Its x is this one, which is 3 minus Z. Right? Okay. So, the shear at F is 0. So, the shear at F is equal to the summation of shear or vertical force from left or from A to F. And this is equal to 0. So, it is minus 7.5 times 2 plus 10 plus this area. Take note this is plus because this is upward. But this area is a trapezoid. So, it would be average height 20 plus this. So, that is positive. 20 plus this one, which is 20 over 3 times 3 minus Z, that one. So, over 2 times the width. The width is Z is equal to 0. Solving our Z, the Z equals, so this is 0.2614 meter. So this is our Z. So I will instead just solve the moment here instead of solving for the area of this. So considering this diagram, the moment at F is going to be equal to, moment here, minus 7.5 times 2. So, minus 7.5 times 2 times its moment arm. So, this is minus 7.5 times 2. The moment arm here, this is 1 meter plus 2 meters. So, this is 3 meters plus Z. So, this is 3 plus Z, which is this one. I will store it in my memory. So, shift store C. Okay? Alright. So, plus 10 times this. So, plus 10 times 1 plus Z. Then, minus the moment due to this. Let me magnify this. So, it is something like this. Right? And it is upward. So let me split this into 2. This is 20. But what is this? This is 20 over 3 times 3 minus z. 20 over 3 times 3 minus z, right? So, substituting z here, this is going to be 18.26. This is 18.26 kilonewton per meter. So, therefore, this one is going to be 1.7426. Okay? So, that is this one. Okay? Now, computing the moment here at point F due to this load, I will just take this as this rectangle, this one, the 20 by z rectangle, minus this triangle. So, the resultant for this is, let me call this R. The resultant for this, dahil minus, it would be down. Right? So, let me call this T. So, computing now the moment at F, that would be due to this, minus 7.5 times 2, that's the area of this one, times the moment arm from here to here is 1 plus 2, 3 plus z. So, this is times 3 plus z. So, I will just express it in terms of z. I store this value in my calculator as alpha c. Okay? So, plus the moment due to this, that is 10 times 1 plus z. So, plus 10 times 1 plus z, right? And then, due to this trapezoidal load, R times z over 2. But what is R? That would be 20 by z. So, plus 20 by z, right? Times z over 2. So, that is z over 2. Minus the moment due to t. T is 1/2 of z by this. By 1.7426. I stored this in my calculator as A. So, that is T times 1/3 of Z. So, this is 1/3 of Z. You compute this now by substituting Z is equal to this. So, you'll get here the moment at F is equal to, let me just isolate it. So, it is equal to, so this would be minus 35.6435. This one is going to be minus 35.6435. So, let me just reposition this. So, this one is 35. This is minus 35.6435. So, this is negative area decreasing, negative decreasing this one. Take note that this is point of zero value. It will reach the zero value, that is point of tangency with the horizontal, something like this. Okay? And this is second degree. This is third degree. Okay? So, the maximum negative moment is already this one because that is the point of zero shear. This value, I will continue the moment ordinates here. So, the moment of minus 35.6435 plus the area of this is a positive area and it is a spandrel because this is point of tangency with horizontal. But this is the spandrel, this is parabolic. So, the area of the spandrel, second degree, is 1/3 base height. This one is 2/3 base height. So, it is going to be 2/3 of the base. This is 3 minus z. Multiplied by the height is 25. Computing this, substituting z is this one, you'll get, so this is 10. Positive 10. So the moment here is positive 10. So this is positive increasing. Positive increasing is this one. And it begins with 0 value. It will begin here. Something like that. So it must be this one. This is second degree. This must be third degree. Right? So there will be a point of 0 moment somewhere here. Okay? Or that is known as the point of inflection. So the maximum negative moment is minus 35.6435. The maximum moment here is 10. You get it? So this is plus 10. So in order to zero it, there must be a downward 10 here, right? Meaning, at this point, there is a moment of 10, a downward moment, negative moment, right? So, it means here, this must be a fixed support, right? And we have here a moment that is equal to 10. You get it? You follow? Okay? So, you may copy.